Hello everyone, welcome back to my channel Easy and Inspire. In today's session I am going to discuss about conversions of flip-flops. Previously we have seen different types of flip-flops like SR, D, JK and T. So in that I have mentioned D flip-flop is modified version of SR, JK is modified version of SR like this. So in today's session I will discuss all the conversions of flip-flops like SR to D, SR to JK and JK to T like this. So in this topic I am going to explain about excitation tables of flip-flops. Listen here, excitation tables of flip-flops. This topic is useful in flip-flop conversions. So first of all I am going to discuss about excitation tables of flip-flops. So let's start. In previous videos we have seen two tables. First one is truth table, second one is characteristic table. So both are different. So in this session I am going to discuss a new table, that is nothing but excitation table. So if you see in characteristic table, you will observe, consider I am taking SR inputs. So two inputs S and R, two inputs, present state, next state. So see here I am mentioning this is the characteristic table, just observe this one. So this is the characteristic table of SR. These two are inputs. This is Q of T, that is nothing but present state. This is next state. So this characteristic table is derived from truth table and state of the SR flip-flop. So different states like no change state, reset state, set state and invalid state. Based on that values I am mentioning present state and next state values here. Okay. So here to design this excitation table we need characteristic table. Listen carefully. To design excitation table, characteristic table is required. So you need to learn how to design a characteristic table. So for previous flip-flops like SR, D, JK and T. So learn how to design a characteristic table. So then excitation table is very easy for you. Excitation table. Listen carefully. Truth table and characteristic table both are different. Similarly, excitation table is different from characteristic table. So characteristic table is required to design excitation table. So here I am going to mention what is an excitation table. Excitation table is nothing but, so it is also a tabular data in which, listen carefully, in which, so present state Q of T, next state Q of T plus 1. See, present state and next state are given. We need to mention the inputs for these combinations. So we need to mention, we need to represent the inputs for the combination of present state and next state. So you will need to know all these in next slide. Here I am going to explain you about how to draw excitation table for SR flip-flop. Listen carefully. This will help you to draw the remaining for JK, D and T. So I am going to explain this and listen very carefully. So first of all, we need to consider characteristic table for SR flip-flop. So for this flop, so we are taking characteristic table. So this characteristic table I have considered from previous videos like SR flip-flop video. So this characteristic table I have taken from SR flip-flop. So if you observe here, we know that, so SR characteristic for 0, 0, S0, R0 condition is nothing but no change condition. So next S0, R1 condition, listen carefully, S0, R1. So it means here R is highlighted, that is nothing but reset condition. S1, R0, see, S1, R0. Here S is highlighted, so output is setted, so that is set. S1, R1, that is nothing but invalid condition. So we know all these conditions. Based on this, I have derived next states. So for the first one, S0, R0, if present output is 0, next output, so next output is no change, so 0. If present output is 1, no change. So next output is also 1. So these two are completed. Next, S0 R1 condition. If present output is 0, next output becomes resetted. So it is resetted to 0. If it is 1, again it is also resetted to 0. So based on these characteristics, so characters, we are defining all these values. S1 R0, that is nothing but set. So whatever the present output, either 0 or 1, whatever it may be. So the output, next state output is going to be set to 1. Now listen here. From this, how I am going to derive this excitation table? First of all, 0 0 0 0. So I have already discussed excitation table contains present state, next state combinations. For these combinations, you need to write the inputs. So these two are inputs, SR are inputs. For these combinations, you need to mention inputs. So first combination is 0 0 0 0. See here 0 0. Next, for these combinations, if you observe, okay, I'll type in 0 0 S0 R0. So for these combination inputs are S0 R1. If you observe these two, S0 S0, these two are same. So I kept here S0. R is 0, R is 1 here. So both are different. So I have placed X either 0 or 1. So first combination is completed. So observe same next combination 0 1. Where is that? Here. So see 0 1, only one combination. So 0 1 I have placed here. So for this one, inputs are S is 1, R is 0. See here S is 1, R is 0. Next one 1 0, only one combination. Okay, S is 0, R is 1, 0 1, 1 1. So here 1 1, 1 1, two combinations. See, so I have placed here 1 1 combination. So if you observe here 1 1 here 0 0. For this one 1 0. In these two 0 is common. So 0 is placed here. So here 0 1. So placed X here. So this is the excitation table for SR flip-flop. Similarly, you need to derive excitation tables for JK flip-flop. See, JK flip-flop characteristic table. I have taken this from JK flip-flop video. So 0 0 combination J0 K0. Again J0 K1. J is common 0. K is different X. Similarly 0 1 2 1 0 1 1. So like this you need to derive for D 0 0 0 1 1 0 1 1. So for this combination 1 1 combination input is 1. 0 1 combination 1. 1 0 combination 0. See 0 0 combination 0 0. So like this. Similarly for T flip-flop. So 0 0 0 1 1 0 1 1. So learn how to draw excitation table clearly. So this will help you to convert any type of flip-flop. So SR to JK, JK to SR, or whatever the conversion may be. Now we will see how to convert one flip-flop into another. See, flip-flops. So there are 4 types of flip-flops we know: SR, D, JK and T. So we can convert SR into remaining 3, D into remaining 3, JK into remaining 3. Like this, total possible combinations are 12. But here I just mentioned only few, because these few combinations, these few conversions are very, very important among all the 12 combinations. So observe, total 12 combinations are possible, but I have taken only few. These are very, very important combinations. So in these combinations, I'll explain 3 or 4 combinations in this video. First of all, we need to know the conversion procedure. So listen, if we want to convert SR to JK, So I have taken example here, SR to JK conversion. So find out source flip-flop and destination flip-flop. Here, this is the source and this is the destination. So find out source and destination. And now draw the truth table for destination flip-flop. So better you can take characteristic table. So it is better compared to truth table. So draw characteristic table of destination flip-flop. So for JK, draw the characteristic table and extend it as excitation table of source. So consider characteristic table of JK, excitation of XR and combine these two. So it is very easy and I'll explain in next slide. And now draw K-map for source elements. Source elements are here, source, this is two elements S and R. K-map for S and R. You need to draw K-maps for source elements and then find out expression for S and R. Now draw the circuit diagram. So according to the expressions. So study this one carefully and I'll explain the procedure now. Listen. First of all, conversion SR to D flip-flop. Here source is SR, destination is D. See here, destination is D. First point is, so draw characteristic table of destination. So characteristic table of destination. So this is the characteristic table. So we have already seen in previous slides. And this is the excitation table of source. See here, this is characteristic table of destination. This is excitation table of source. Now you need to combine these two. So first of all, consider this one, same as this. Now for these combinations, see here, for these combinations, write down input combination 0, 0. So for 0, 0, S is 0, R is X placed. Next here 1, 0, not 0, 1, 1, 0. So for 1, 0, 0, 1. See 0, 1 I have placed here. So listen, draw this one as it is and extending this to SR. So for 0, 0, S is 0, R is X. For 1, 0, S is 0, R is 1. For 0, 1, so for this combination, S is 1, R is 0. For 1, 1, X and 0. So this is the final table. So destination table is extended and excitation table is derived. So this one is excitation table. So this one is, so up to here, this one is destination, sorry, characteristic table. So both are combined here. Now you need to draw K maps for S and R. So K maps for S and R. So consider these two values. Always remember, consider Q of T. No Q to T plus 1. So don't consider Q of T plus 1. Consider present state and either whatever the input may be, either JK or T or D, whatever it may be. So Q of T and the input values here. So consider these two and see here. S is 1 for D1 Q of T 0. Listen. Next S is X for D1 Q1. So listen carefully. First K map for this one. Only these two values. Don't consider these values. So see, this is the K map for S. So D and Q of T. D and Q of T. Don't consider this one. So 1, 0. So 1, 0, 1. 1, 1, X. 1, 1, X. So K map for S, this is the one. And from this, so S value, S is equal to, this means D bar, this is D. K map, you know already. So S is equal to D. Similarly, draw K map for R. 0, 0 is X, 0, 1 is 1. 0, 0 is X, 0, 1 is 1. So this is nothing but D bar. So S is equal to D, R is equal to D bar. So from these values, draw logic circuit or block diagram of SR flip-flop. Here I have considered only block diagram representation. you can draw logic circuit. So here observe, this is SR flip-flop. This is SR flip-flop. So I am extending this here. D is S. So directly S is given to D. And R is D bar. R is D bar. Here it is D. It is D bar. So this is nothing but total circuit is D flip-flop. So this is clock pulse. So SR flip-flop now converted into D flip-flop. This is the conversion from SR to D. So now I will explain one more. JK to D flip-flop. So source is JK, destination is D. See here, source is JK, destination D. Characteristic table of destination, excitation table of source. Combine these two. So first of all, take this one as it is. So as it is I have considered here. Now for these values 0, 0, 0x, 1, 0, x1, 0, 1, 1x, 1, 1, x0. So for these values, mention the values by considering this 0, 0. So 0, 0, 0x, 1, 0, 1, 0 is here, x1. Similarly, write down the remaining. Now, same k maps for j and k map for k. So 0, 1. So combination of only these two. Don't consider q of t plus 1. So again, I'm explaining here. Listen. Don't consider next state, present state and D. So see here, x, 1, x, 0, 1, 1, 0, 1, 1. See here, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. So I have drawn all these values, and so this is the k map for j, k map for k. So draw k maps from the above table, from this table for j and k. So see, don't consider 0. We need only 1 and x. X means either 0 or 1. See? So consider d and q of t. So I have drawn k maps for these two, and this is the possible combination. No need to consider x because this is don't care condition. Again here. So here j equal to d. Again here j equal to d bar. Sorry, k equal to d bar. So this is my JK flip-flop block diagram. I am extending this j equal to d. So d is directly going to j. D inverted here. So k equal to d bar. So this is my D flip-flop designed from JK. So similarly, you can design any type of flip-flop from whatever the flip-flop you have considered. See here, this is one more. D to T. So source, destination, T. So destination, characteristic table, source, excitation table. Combine these two. Next one, from this one, consider these two values. So 1 and 1 here, only 2. 0, 1, 1, 0. See? 0, 1 and 1, 0. T into Q of T. T bar into Q of T. T into Q bar of T because it is 0. That is nothing but XOR operation of T and Q of T. So D equal to T XOR Q of T. So this is my D flip-flop. So D input is equal to T. Q of T is nothing but present state output. So see, this is feedback given to XOR gate. T XOR Q of T, that is nothing but D. This is my T flip-flop designed from D. So D to T conversion is completed. This is my last conversion in today's video. So listen carefully. This is from SR to JK. So in previous videos I have explained just JK flip-flop is derived from SR. So we don't know how it is derived. Here I'll explain, listen carefully. SR to JK. So source is SR, destination is JK. For destination, characteristic table is written, and for source, excitation table is written. Now combine these two. So how to combine these two? 0, 0, 0, 0. Here you need to mention combinations of S and R. for 0 0. See, 0 0 means 0 and R is X. Again here 0, R is X. 0 1 here, 0 1 here. 0 1 1 0 1 0 1 0. Similarly, place the remaining and draw the extended table. So, characteristic table extension. See, this is the extension. Now, from this table, consider these three values. I have already explained. Don't consider q of t plus 1. Just up to q of t you need to consider. So, these three values. Draw K map for S and R. So, here x1, x1. So, this is for S. This is for R. See here, x, x1, 1. See, I am taking only SOP form. You can consider a POS form. Just take SOP. It is simply easier for you. So, from this, see, ignore this value. Just consider this combination here, this combination here. It is J into QT bar. Here K into QT. So, my expressions for S and R. So, now from these expressions, I am going to draw logic diagram or block diagram. See here, SR. So, J into QT bar. QT bar is this one. Here, R is nothing but K into Q of T. So, we have already seen this diagram in JK flip-flop. So, now we can conclude that JK flip-flop is designed from modifying SR flip-flop. So, this is about how to convert one flip-flop into another. So, you can try all the remaining flip-flops. And in next session, I will explain analysis of sequential circuits. Thank you.